Welcome to this presentation of the EPFL Canopy Pavilion. My name is Pauly. I'm a professor of computer science at EPFL and I'm the director of the Geometric Computing Laboratory, GCM. And on behalf of my co-authors, I would like to present our project, which is a truly collaborative effort. And since the time we submitted the paper, a number of additional people have joined the project. But I would like to specifically highlight the contribution of Isvoranu, who's really the mastermind behind this project. To give you an idea of what this is about, here is a video overview of the pavilion. So this is a permanent shading structure that covers a part of the barbecue place at the central place at EPFL campus. And this project is remarkable in that it really represents everything that this conference, the Advances in Architectural Geometry, stands for. So it combines geometry and mathematical reasoning, advanced algorithms with an application in architecture and engineering and brings all of these components together. But it is also a real structure, and that means there's additional constraints, in particular budget and timing constraints, which unfortunately led to the construction to be delayed several times. So we anticipate the opening of the pavilion for this year in the fall instead of the summer of last year. But let me walk you through the different components of this project, starting with the architectural context. So as I mentioned, this is a permanent structure that will be erected on the campus of EPFL. Here you see an aerial overview. And if I zoom in a little bit, you see the location at which on the campus at which the pavilion will be built. Here's a top-down view. And again, you see that on the right, there is the Rolex Learning Center by Sana. On the left, we have Kengo Kuma's design for the EPFL pavilions. So the location of our structure is in a very prominent place, the Place Cossonday, which is the central gathering space of campus. And as you can see, a central theme on this place is the circle. So we also adopted that as sort of key structural element and design element for our pavilion. In addition, the silhouette and the shape of the pavilion was inspired by the mountain silhouettes in the background across Lake Geneva. And because this place is relatively new, there are no large trees, but we wanted to create a shading experience that is reminiscent of trees. So that means we wanted to design a permeable structure, an open structure that is composed of individual aluminum panels in a multi-layer configuration. So we get a sort of playful shadow, somewhat reminiscent of a natural tree, as you can see in these zooms in here. But this structure also has a very interesting geometry. And I want to start a little bit giving you a background on the geometric methods that went into the design of our pavilion. The key concept that we exploit here is the fact that we wanted to design a double curved structure that can still be assembled from simple components in the plane and then mounted into its final shape. And in order to do that, we use so-called deployable auxetics, a structure that has been studied quite extensively in recent years. This structure is based, in our case, on a triangular linkage, as you see here on the left, which can be abstracted mathematically as a conformal map. This triangular linkage exhibits auxetic deformation behavior, which means that as I stretch it in one direction, it will also expand in the other direction. And it does so in a uniform way, which is exactly what a conformal deformation captures. And this mathematical abstraction then allows us to connect the scale of expansion or the expansion rate to the curvature of the surface, which is then finally the basis of a computational algorithm that tells us how we need to structure the material in the planar state. And in particular, in our case, this means how we need to scale the individual triangles in a spatially varying way such that the surface deploys to the desired target state when it is maximally expanded. I will not go into too much detail here about the computational methods. There's a series of papers that describe these in detail, including one paper that appeared at the last AAG conference, in which we incidentally already sketched the idea of a shading pavilion, but here designed as a hanging structure. Now, for a real physical building, such a structure is maybe not ideal because it will move around a lot in the wind. And for this project, we wanted to build a structure that is more stable. This led us to the idea of designing a membrane surface. So as I mentioned earlier, the auxetics assume their target shape when the surface is maximally expanded, when the material cannot stretch any further. Now, such a surface is stable if any additional deformation would lead to more expansion, because the material is maximally stretched, it cannot expand anymore. But if any deformation would lead to more expansion, it also cannot shrink. And this, of course, is the definition of a minimal surface. So this motivates our structure, which here is sketched abstractly, to design it as a minimal surface spanning the boundary ring, the circular ring that defines the boundary, and then having a two-layer structure that is separated by a compression pole. So as a minimal surface, this structure will actually be stable. The orientation of the compression pole is not accidental, but we set it to meet sort of the highest point of the sun, meaning the direction of the sun at the solar noon during the summer solstice at the specific location that we're located at. So there's a link between the sun and the design in this sense. So auxetics are a sort of geometric principle for the design, and in particular the effect that they can be deployed from a flat state to the desired double curvature target state. Now, I want to briefly illustrate how we compute these things. Specifically, we start with an initialization as a planar regular auxetic linkage, and then we use a variant of sort of dynamic relaxation, in this case based on projective dynamics, that also incorporates actually the pre-tensioning necessary to keep the structure stable. So this surface will then, of course, deviate from a minimal surface, but it will be a surface under tension everywhere. Now, the actual main function of this pavilion is to provide shade. So obviously we can study the shading performance in this sort of video mode here, where we just show the shift of shadow during the day. But what I found specifically interesting in this project is to explore this performance in VR. Now here I can only show you a video, of course, but the experience is truly mesmerizing. This helped tremendously in the design to understand the shadowing capacity of these plates. Now, the design initially was composed of triangular plates. I showed you this triangular linkage earlier, but we increased the triangle sizes into these hexagonal shapes in order to provide more shading capacity. And in order to figure out what is the right level of shade versus translucency, this VR application that we built really helped us in the design process. So for me personally, this was the first time that VR really helped make design decisions by being able to immerse ourselves into the design directly. Now, finally, there are, of course, engineering aspects to this work. This is a structure that is composed of aluminum plates mounted on a steel support structure. And interestingly, the connections between these plates are all identical. This makes fabrication much simpler, and the plates themselves are all different. This ensures this auxetic deployability into the desired target state. So plates are cut with a laser anyway, and therefore the different shapes don't cause any additional complexity, but the connections between them are all identical. Now, these connectors, of course, need to make sure that the structure is stable. Our initial concept was actually very simple. We wanted to use a simple steel wire to connect two neighboring plates. And such a connection is necessary in the sense that it needs to allow in-plane rotation of the plates, as well as torsional rotations. So if you zoom in, we wanted to use a simple wire like this. We did some preliminary finite element analysis, which confirmed actually that that kind of steel wire is sufficient to support the static forces acting on such a surface. However, once we went into sort of more serious analysis and incorporated a structural engineering company, we realized that we needed to strengthen this connection significantly. And this is due to the fact that, first of all, we need to account for dynamic loads in worst case scenarios. We also need to account for wear and tear. As I mentioned, this is supposed to be a permanent structure. So over the years, this wire would probably very easily degrade due to motion in the structure. The final connectors are substantially more, expanded and of course strong. So these are custom-built steel connectors, but they're all identical. And in particular, they support the in-plane rotation of the plates as well as the torsional motion. And here, for example, you see close to the plate that this torsional rotation is really needed in order for this pre-tensed structure to assume its desired shape. So in conclusion, what I find specifically fascinating about this project is that these different aspects, geometry, algorithms, engineering aspects, the architectural vision, all really need to come together, and these different competences need to come together to realize a project at that scale. Now all that remains is for me to invite you to come and visit us in campus. The inauguration of the pavilion is planned for October in this year. Unfortunately, at this point, I cannot show you any real physical results. Construction and fabrication is about to start now, but visiting campus is interesting anyway, because you'll see a lot of interesting architecture. You will accidentally also have the chance to see another installation that was premiered at the Advances in Architectural Geometry in 2012. So if you come on a sunny day, you can also see this structure here. So I'll invite you to come and visit us. We will keep this website up to date, canopy.epfl.ch. Once construction starts, we will augment it with photographs and of course all kinds of documentation, including 3D models and digital plans. So if you don't have a chance to visit us on site, you can at least experience the pavilion from afar. Before concluding, I really want to thank EPFL for supporting this project generously with, of course, funding, but also a strong commitment of the people responsible for the campus development. We think it's a great example of using a research demonstrator and showcase how we can bring research that was presented here at this conference into an actual architectural application. Thank you very much.